Hello and welcome to 27th lecture of course on data-enabled tribological engineering from experiments to predictive models. Topic of this lecture is data-driven models for wear prediction. If you remember, first four lectures were more focused on friction and wear. And we know very well that wear is a gradual phenomena which causes a surface degradation of the material. And because of that, dimension will vary, and if the dimension go out of the tolerance range, we need to replace the component. We have studied some conventional wear model like Archer equation, which depends only heavily on load as operating parameter, operating speed, hardness of the soft material. And we do also require one wear constant, or we call it calibration constant, which needs to be digged out, or maybe say we need to find the value of that coefficient from the experiments. In this situation, we have taken a lot of assumption, particularly for those conventional equations. Reason being that we are assuming there will be a kind of a load which is not going to change significantly. Another assumption comes something like a steady state circumstances. Load will be uniformly distributed. Material will be isotropic properties, which generally doesn't happen in actual cases. So that's why we really require a machine learning algorithm. Reason being the machine learning algorithm can forecast surface degradation by utilizing data-driven algorithms, which are current topics for the maybe say 23rd lecture onward. Those models which we are getting from machine learning algorithms, they are basically supervised. Of course it can be unsupervised, but we are giving more emphasis on the supervised learning, and they try to reveal some sort of pattern which are available even in data which are available in the literature. So what we are saying that we can dig out trends from available data, we can develop some sort of correlation, and we can implement those correlation and apply experimental results on that. And we can correct, we can modify those algorithms or results, we can really forecast. So this complete lecture, this present lecture is on that. How do we do that? But before that, let me give one of my reference of maybe a publication reference, which was published in 2023 in Tribology International. We tried to figure out what will be the wear of spur gears. And of course, we use a stress factor in that. That is what we call accelerated wear test. We have implemented some sort of misalignment in radial direction, axial direction, and angular direction. So we can say in that we did an accelerated gear failure caused by stress concentration resulting from misalignment, because misalignment causes a stress level or high stress level or stress concentration. We developed some mathematical model to give us some sort of force indication because of the misalignment. And we use a new model, something like a slicing of the gear teeth, which we know that in when we go for the deep learning or maybe CNN, we go with slice by slice. So that kind of method. And of course, we added Archer-Weir equation, which in this present lecture, I'm just saying it has a limitation, and we need to change that. After doing all this mathematical modeling and estimating the results, we verify the results against experimental data. Of course, we have a real gear setup, as well as we did some experiments on pin on disk machine. We got some sort of SEM images from wear particles as well as failed components, and then we try to develop some sort of correlation. I use the word slicing. Slicing something like that, slicing of gear. If you look at the gear teeth has a thickness, so we are dividing a slice in slicing that gear teeth into a number of pieces, and each slice is being estimated, and we are moving gradually. So what will happen even we can capture some sort of localized effect when we are going for this kind of slicing. However, major drawback is this, as I say, Archer-Weir equation we studied earlier in a lecture 4, that it is a wear volume divided by sliding distance into the normal load divided by hardness, and we say wear coefficient over here. Just to reduce the effort, this we use a specific wear coefficient which is a k by h, and then we, after doing experiments, we estimated this wear coefficient as a 6 into 10 to minus 10 mm square per newton. You know very well that this wear coefficient k is a non-dimensional, but when we are choosing this specific wear coefficient which has a dimension, and that's the we doing all of our experiments, we estimated that wear coefficient k is a 6 into 10 to minus 10 mm square per newton, but this is a kind of assumption. And in recent days, or with the way machine learning is emerging, this kind of solution may not be correct, and we need to really refine this solution. We need to come up with a much better results. That's what we are developing some algorithm. We are going ahead with image analysis. We are going ahead with the CNN or deep neural network programming. So what we can say, we really require a better wear production model, and it is known very well that whatever we have been doing earlier, it's basically failure analysis. We fail the component and we try to diagnose a failure, which is not going to be in the future. In future, we want to avoid any failure, and particularly unexpected failure. We say we do not want any failure, and unexpected wear has to be completely eliminated. Reason being, it causes undesirable downtime, it causes a severe financial losses. So this approach has to be completely eliminated. For that purpose, we require a good estimation of wear, and if you use the Archer equation, that gives the average. So that turns out to be challenging, and we really require a very good mathematical model or machine learning model, and supported by the experimental results, so that we can mitigate all the wears, because we need to understand what kind of phenomena. And then in addition, instead of going ahead with the too many experiments, we want to conduct only few experiments. Reason being, conducting experiment itself requires a cost. Not only that, it may cause also contamination, or it may cause some sort of additional problem. So we need to really understand those. Let me start with that. We say there is a one challenge. Challenge one: do I need to go with offline or online? Previous slide, what I show the paper, that was basically offline monitoring. We fill the gear teeth, and then after that we are cutting the gear teeth, and we are going for the SCM imaging. We are estimating how much wear has occurred, how the surface roughness has changed, how much the mass loss. So all are offline, not online. But now current trend is going more and more on online to monitoring. So we need to shift from offline to online. It's not so easy moving from offline to online. Reason being, we really require very good sensor, we really require very good data acquisition system, we really require cleaning of the things. So these are the important aspects. So what we can say in offline sampling, which was very common, or maybe previously it has been utilized in a better manner, or we say in extensive manner. Now it is turning out to be labor intensive. It is because of the human interaction. Sometimes we do have some sort of contamination, or it also requires a sample preparation. Many times a sample which is prepared, and if you are investigating after 4 hours, 6 hours, 10 hours, that sample gets contaminated. Even though you cut the gear teeth, and then after that you go for estimation, it will get oxidized, some other contamination is coming out. So which was not a cause of the failure, but when we diagnose, that kind of a failure also has been estimated, or it comes out. So we need to really get rid of those things. Now coming to the online wear analysis, do we have also some advantages? As I say, that we can get everything in situ, and then we can get a much faster result at a much lesser time. However, for that purpose, we really require a non-destructive techniques. We really required a vibration analysis, which is very, again, very common. People have been utilizing for the more than 60-70 years. But question comes, will I be getting everything from vibration analysis? Or even the lubricant monitoring, will I be getting all estimation from lubricant analysis? Or sometime we are now starting with optical scanning of the surface, which is getting surface degradation. We may be discussing more about the wear debris analysis, whether that is also sufficient. Now another technique has emerged also, infrared thermography. Reason being, we get a thermal image and we analyze that. So there are very many entities available, and we say that each technique has a unique advantages and disadvantages. Question comes, are we able to integrate two or three entity and then come up with a better results. For that purpose, we again really require a data fusion, and we really require a more and more knowledge for that. So what we see in this situation, often people say that data acquisition is not that difficult. Initially, we will be procuring lesser data. As the surface gets more and more degradation, we will be going for the faster speed, and more data will be required that time. But question comes, what is the borderline? How do we go ahead? Naturally, it requires better algorithm, better understanding, so that we can move from a lesser data to more data, more frequent data. Naturally, that need to be incorporated. Another technique which we also have to some extent covered is a condition based maintenance. We say we do not change the component till it comes to the stage where it really is moving out of the dimensions, or maybe say dimensional tolerances are moving out of the boundary, and then we nearly require it. However, in this major emphasis has been given on the faults instead of the failure. We say we diagnose a faults, not a failure. Failure is a final thing which need to be changed. The component need to be changed. However, if we diagnose faults at the beginning itself, we can do a number of corrective action that will help us making a better decision related to maintenance, and it will overall causes lesser economic losses. It will be much more useful. However, our aim is to make a component which doesn't fail at all. And if there is some chance of a failure starting or inception, then we need to diagnose that fault and do corrective action. If it is possible, actually the survivability of the component will be very high, and sustainability will be really met properly. Now, this NDT techniques I have already covered in other course. The course name is corrosion, environmental degradation, surface degradation, and I'm showing the slide which already I covered in lecture 5th. So if you in again revisit this kind of lecture 16, 17, 18, 19, 20 of the course, other course, you will get a better knowledge about the NDT, and then we will be able to come up what is the really drawback of each NDT and what are the advantages, so we can go ahead with a better selection. Again, alone one or two technique may not be sufficient. We need to go ahead with a more number of techniques, so that we can really take a very good decision or favorable decision. Now coming back to this present lecture, we say wear production. We already given challenge number 1. What is the second challenge? Second challenge is that we get a too many data. There's abundance of data that sensor generates, and we need to process that. Last time we learned something about ANN. We said that we can go ahead with ANN to provide a precise and consistent measure, particularly related to the wear, and which is related to the industrial component, because we have many the wear failure pictures available in literature. And then if we can scan, if we can train our ANN, then it will really be able to give a better results. So what for that purpose we required integrating online sampling with the data driven models which need to be generated, so that we can enhance predictive accuracy. Because many times if I'm looking at the value from a one angle, if I go ahead with a 90-degree face, I will find something different. So predictive accuracy will reduce. Even though when we are publishing paper, we are selecting few samples, but in reality, in real case, it may not sustain that much, or maybe it will not be able to give that kind of accuracy. So we really require more and more better and better productive model, or maybe say data driven models, which really can provide a predictive accuracy. It can reduce it downtime and optimize the maintenance strategy. So this is what we really require, and still we don't have a complete solution. It is still a kind of research phase, and we are being continuously trying to improve it. And one of the best thing is that exploration of their debris, because we know that material will get degraded when the surface is getting some loss of the material from a surface. Naturally the wear debris are coming out of the surface, so naturally we need to think about what is the generation rate of the wear debris. Can we classify wear debris so that we can say that it is abrasive wear, adhesive wear, it is happening because of the lack of lubricant, or it is causing because of the asperities, or it is causing because of the material compatibility, or maybe some other non-materials are coming into picture, or maybe the dust is coming into as a third party, or maybe the third body abrasion is caused because of that. In addition, are we able to generate a regression models so we can estimate with the time how much wear will increase, whether after 5 years, after 2 years, after maybe say 2 months, what will be the wear rate, and then how much life will be remaining, or we say the residual useful life will be there. So we can estimate the proper thing, and we can take a proper decision. So what we say, it requires understanding feature like a size. Are we able to really measure the size of the wear debris? Many times we say that zero wear with the size of the debris is almost negligible, and is kind of the polishing action. So are we able to distinguish between the polishing action, which is not causing a material to degrade or surface to get degraded, but it is causing the improvement in the surface, it is going to be more useful. So we should not stop there. If something is useful for the survivability of the component, that should happen. So are we able to estimate the size? Are we able to find out what is the size distribution? Are we able to find out what is the shape of the wear debris particle? Because these all are the crucial. We can really classify, we can establish the regression models, and then we can say that we can generate better solutions. Then another good point comes is something like a pre-trained ANN model. In last lecture, I also given some sort of pre-trained ANN model, which MATLAB has a number of algorithm. You go ahead with any of the pre-trained models. One or two will be covered in this lecture also. So when we go with that, major thing comes what is input and what is output. And those mostly pre-trained ANN, they are more like a black boxes. We are not able to really understand much, but once it is established, we can really utilize for our experimental results. But if we are not very clear, then we need to write some sort of custom codes to understand and then improve the results. Once everything is clear, then we can go ahead with the pre-trained ANN models. We know that number of layers in pre-trained ANN will be something like a 140, 150, 200 layers, which are very important because we really want to diagnose each and every feature of the wear debris, even the surfaces from where it is coming out. For that purpose, where this pre-trained ANN will be really required. However, when we are going for the custom coding, we really require more number of data. Often we lack those data and we need to generate more. However, we can learn from literature, and we can dig out that information. We can digitize those information. And in one of the previous lecture, I also mentioned that how to really extract the information from literature also. So what we say, the future of your production lies in embracing online automation for the industrial efficacy, so that we can really do each and everything online, and whatever we learn, we are able to really get data driven models which are able to provide some decision or act on a force speed. They are able to regulate those. So that's the future, and we are trying to give that information. I'm not saying this lecture is complete by any sense, so I'm giving relevant information. Quite possible future more and more advanced technology will be available, and then this is possible. So I'm just thinking that this is a possible, and that's why I'm trying to show the results, or maybe say hypothesis from that point of view. And now if we are able to get those kind of equipment, better image processing, better and online sensors which are providing a good results and the good data fusion, so that we get results from a three sensor and they are getting aligned with each other, so that we have our confidence level is on a higher side. But that's the future, and almost every component need to accommodate this kind of online automation, and then only the results will be much favorable to engineers. Now coming to the wear debris analysis, we say these are the debris come out because of the interaction. Now we can think about something like the sliding motion, and the wear, whether we need to divide the wear debris as a sliding wear or rubbing wear or some sort of rolling wear. We need to really understand. It may vary from one situation to another situation. However, we need to also know whether whatever the debris particles are coming, is it really in a running in phase, or is it really in a useful working life, or is it in a failure zone? If you are able to differentiate, then our predictive model will be very useful. Now major question comes even in running in case. Initially I'm applying 100 Newton load, running in maybe over, maybe say after 200 hours. But if I increase the load by the delta, maybe say even 20%, quite possible again the running in will start. It's not going to be and the initial level only. So we need to really think whether are we able to really predict those kind of things appropriately. Sometimes we give some sort of suggestion, or if number of part and the particle size is more than 25 micron, that means there is a kind of shift from mild wear to severe wear. But again, that may not be correct because it is related to the size. So that's why we need to have a good algorithms, good predictive algorithm, which can really find out the particle size, shape, and then also kind of alarm that what is really the size, whether it is really increasing. Allowable tolerance limit is suppose 50 micron, and particle size is coming more than 25 micron. Naturally, the 25 micron is going to be very severe. However, allowable limit is something like a 500 micron. The 25 micron may be say depending on the distribution, out of 1000 few particles are coming 25 more than 25 micron. I may not worry that much. So this is very important to understand. And moreover, we say that when we are going ahead with the data driven models, we need to have some sort of relation between operating time, size, and type of the weird particles. If with the operating time number of particles are continuously increasing, which would many times we call the trend analysis, that naturally the wear is increasing significantly, and then we need to take appropriate care. Now, as I mentioned about ML algorithm or machine learning algorithm, now here good point is that once we train it, or once and then we develop algorithm that can be applied even for metal, alloy, and polymers. However, if you look at earlier physical law, there are some sort of limitation. Few will be only applicable for metal, few will be able to get a good result for polymers. So there will be a kind of a different material, different relation. Our machine learning algorithm, only the constant will vary, or say whether the coefficients will vary, bias factor will vary, weighting factor will vary, but then everything will be done in ML only. We are not really changing. It is going to change as per the situation. It's going to change as per the operating condition. So we don't have to change algorithm. Once algorithm is established, we will go with that. So that's why we say it is applicable for the metal, applicable for alloys and polymers also. So these are the important. However, sometimes we give a operating condition like a load, speed, sliding distance, temperature, friction coefficient, kinematic viscosity. Whatever we have learned earlier, that whenever we give kinematic viscosity, it is basically for the lubricated wear, or where the at least some sort of hydrodynamic or elastodynamic lubrication is going to play important role. If that is not, then kinematic viscosity may not be really requiring. Coming to the friction coefficient, when we use a friction coefficient, it is basically for the boundary lubrication and mixed lubrication. Otherwise, we may not really require. Again, this may be input, or it is coming as an intermediate input from other sensor. So we are trying to establish a relation between the two sensors also. Same thing in the operating temperature. Now initial operating temperature which where we started, and then how temperature is increasing, if we are keep getting that information, and that is affecting the viscosity, so we are able to establish relation. So many times we really require these parameters and relation, or if we don't have a relation, a separate the model, maybe ANN model also can be implemented to get overall good correlation between the models itself. And then we need to have some sort of ANN model that can forecast the wear volume appropriately. Here we are using the word friction coefficient. We are not giving a more weightage to minimizing wear coefficient. We are giving more weightage to the minimizing the wear rate. However, if the minimization of the friction coefficient is being emphasized, then naturally algorithm will change. If we require both together, then algorithm will change. So ANN model will change as per the requirement. What is our aim? But it may not change for the metal or may polymer, maybe reason being importance of one parameter is becoming more compared to importance of other parameter, but that importance will be decided by ANN model itself based on experimental reading. We don't have to change our own. Now this slide I'm also repeating, which we explored in lecture 18. What we say, what is the future? Future is a digital twin. Now, digital twin says that whenever the even the particle, which is this is all three are the aberration related, the particle is moving. Now, these flags which are aside, which are will shown on here. Now, this flowing fact we are showing that material is getting displayed one side, this side or this side. Sometime it is cutting a some sort of chip, and that will be having different kind of behavior, and sometime the whole chunk is coming out. That's what we call a spall, a microfracture. All three are example of the abrasive wear. We are seeing the plowing kind of abrasive wear, micro cutting wear, abrasive wear, spalling abrasive wear. Now, are we able to establish this kind of correlation? I believe if we are able to develop this kind of relation, then it will be very good. It will lead to the digital twin, which is really the future, and surface degradation can be controlled once we get this kind of relation. We also covered different wear debris in the lecture 24th, and we found there are some sort of classification. We say rubbing wear will be like this, severe wear will be like this. Of course, you can see here the severe wear and a pitting, there is a quite overlap. So whatever we do, there will be some sort of inaccuracy. Severe wear and fatigue, which is happening because of the sliding itself. That means after sliding, lot of sliding, the it is coming as a fatigue particle, which will have some sort of a texture on the surface, some sort of micro grooves on the surface. While same thing happens when the severe sliding also, but the depth of the groove will be on a higher side. So we in lecture 24th we used this NAPBY classifier, and we classify the wear debris into the cutting wear, into the fatigue wear, into the severe sliding wear, rubbing wear, but there is some overlap. However, easier one is a cutting wear, because we know that aspect ratio in this is the length, obviously whatever the curvature had been shown here will be much larger than other dimension. There will not be much issue as such. Or even getting a spherical particle size, because we know it is getting rounded because of the continuous fund and motion, and is not causing a much wear, but particles which are coming out is a maybe smaller size spherical, so that is also not difficult. So detection of cutting wear, detection of a spherical particle will not cause a much problem to us. However, if it is a causing a this kind of chip which has a many features together, then it will be a more problem. So that's what we see when we have a wear debris and we have taken a CMH, and if we are trying to develop algorithm based on that, we are training the ANN. You look at this particle, develop algorithm, go ahead with the classification, and then in real situation, or maybe say in situ measurement, when we have this kind of debris which are coming out, then it can give information without really going for offline. Many times offline tools have been utilized to find out the wear debris, and maybe the cutting wear, or maybe say the worn out surface of the gear teeth. Here we are talking about online. Whatever the particle comes out, we are able to measure it, or we are able to take a photograph. We are able to go ahead with the ANN model immediately and find out whether a spherical particle is coming, whether the cutting wear is happening, or whether a severe sliding is happening, and then we should take immediate action on that. We should not wait for the final value. That means we know even the final particle which is coming maybe 2 micron, 5 micron, 10 micron size, we need to take action appropriately, so the further wear should not happen, performance should not get deteriorated. So that's also important for us. So now this already we have shown in lecture 24, but now we are trying to develop algorithms on that. So what we say, there is a need of the data driven models in wear prediction. There are 3 points which I have written, 1, 2 and 3. Now why we are using the word? Earlier most of the, if you look at the literature, there is a lesser correlation between the friction and wear. Most of the correlation has been developed under the dry case, boundary lubrication case and mist lubrication condition. And if we have a both importance, friction and wear, so there is a need to develop some sort of relation between a friction and wear, so that we get a better results. And then whatever the data available in the literature and through experiment, are we able to mix together, and are we able to go ahead with a better surface interaction, so that wear mechanism can be explored properly. So what I'm using word here, the data driven models are really required to understand tribology in a better manner. Coming to second one, we have already explored the Taguchi method, ANOVA, and we understood that there are some sort of limitation. And just to overcome those limitations, we also explore ANN. And ANN also requires a data. Only thing, good point in this case is that we will be requiring a lesser number of experiments when we go for ANN model or similar kind of a model in this situation. So we can say it is a cost efficient compared to the all experiments. Maybe we are doing a few experiments. It's not that we are not doing any experiment. We are not going with a zero experiment, because zero experiment will not give a very good results. It will give some data but may not be very useful to forecast their production. So but that's why I say that we really required experiment, but not to that level which were required classically. And that's why we are learning from literature data, we are learning from experiment, we are trying to go ahead with a better predictive model. So we say by utilizing existing data set, computational resources, model reduces the need to mode of costly experiments, and then we are able to predict the wear in proper manner, or maybe say more accessible or more economical method. Third one is accelerated test. Many times we require acceleration, or we require a fast results, and we do not know whether it will shift from one domain to other domain. If you want to go ahead with accelerated prediction process, actually this kind of algorithm will be more useful. Reason being, we are incorporating statistical techniques, we are also going ahead with the advanced computational algorithms, so that more the data can be processed in a fraction of time, and then which was required also related to experimental setting. We want to really reduce number of experimental tests, go for accelerated testing also, so that overall we are able to take a timely decision, and that is very important to minimize failure of the component, so that we are able to take a proper intervention at right time, which is really required. Now, we learn in a previous lecture something about previous lecture something about the deep learning, and here we are trying to explore something like a convolution neural network. It's also the kind of artificial neural network, but we are going with a slightly different process. Obviously, two additional process and one same which we were doing earlier in ANN. So what is this? We say weird debris particle analysis requires a non-destructive testing, and then we want to go ahead with their mechanisms. Now we want to do a classification. Now here we require images. When the classification is related to adhesive wear, which is related to fatigue wear, related to the abrasive wear. In this situation, earlier we were using the ferrography, and then ferrography is something every time you go ahead with the particle analysis, we extract the oil sample, we filter, we say that we remove the oil using the ferrography equipment, and then go ahead with the 3-4 levels of the particle sizes, and then we use some sort of computer based option to say that with a smaller particle, medium sized particle, or bigger size particle. But that was a kind of only experiments. Now we want to include machine learning algorithm to estimate. So initial maybe it's a few hundred particles, maybe we can think about a ferrography, but subsequent we want to remove that, or we say instead of that we can go ahead with online ferrography. Now why these particles have been separated earlier? Reason being that we want to go ahead with the particle coverage, diameter measurements, and then now if it is possible through the image analysis, then we don't have to go for the manual measurement. The only question comes whether is it easy to go ahead with the measurement of the particle. Yeah, there is a possibility, and then we are trying to cover those aspects. So what we say, neural network in this case, which is the heart of the deep learning algorithm, it has already we have learned that this has a number of nodes layer, and we say in a deep neural network DNN we have a more number of hidden layers, maybe some 4 layer, 5 layer, maybe 40 layer, 50 layer, 100 layer. Those things are possible. And then here initially whatever we are covering in this case, we are saying to only from image classification, because this is turning out to be little more difficult image classification compared to regression analysis. So that's why we are trying to cover CNN from image classification, and I'll be covering in next few slides only on the CNN, how do we go with the image classification. Now, coming to the CNN, we say that we are going ahead with the three operation. One is a convolution operation or convolution layers, then pooling operation, pooling layer. Third one is a fully connected layer. Now, this is exactly same what we have already covered in ANN. That means we have a number of neuron connected with each other, and then their weighting factor, their bias factor, those things can be utilized. Now here the two new operation is a convolutional layer and pooling layer. What are those? It's a convolution operation. Basically, it obtains the feature maps. How do we do that? By we are using the word by sliding a fixed size convolution filter. So we'll be using the sum filter. It can be 3 by 3 filter, 2 by 2 filter. We'll be covering in next slide, and then we will be trying to do sliding maybe 1 pixel, 2 pixel, something like what we call a stride. We'll be utilizing that so that we can get a more and more feature, we can extract more and more features from an image which we are trying to explore. And then whatever the output layer, that will go to the pooling layer. So it's kind of a sequential one. The next one is a pooling layer. What are we doing in the pooling layer? We are trying to reduce the spatial dimensions. We are reducing the sizes so that we can retain only the most important information, and of course because of this we will be able to reduce the computational expenses. The computational features, or maybe the expenses, will reduce, and then whatever important feature will be extracted. When we do this kind of thing, we will be losing some information. However, if the by doing iteration, as I say, that when many times we write our own code there, if we are able to understand that some information has been lost, we need to change algorithm. When we go at the pre-trained ANN model for this kind of image classification, we may not be able to know. That's why we say pre-trained ANN are kind of the black boxes. We are not able to really find out each and everything. However, no, MATLAB also helps to export that and then you can analyze, but that will be a little more difficult. So in this case, particularly output of the pooling layer will be passed to the fully connected layers. As I mentioned earlier, that fully connected layer is the same thing what we have done earlier in ANN. It basically classifies or predict the images. Now just to elaborate it, I am taking example of one publication 2020, and they have also analyzed only the image analysis of the wear debris. So what they say, we go with the convolution layer, and convolution layer they are using the word here something like a 5 to 1000 convolution layer. And then convolution layer here, first is that they are trying to extract the only low level features. What is the meaning of low level feature? If I try to give some sort of comparison, like in a human being, we have a nose, we have eyes. So these are the features which can be immediately recognized. So whatever the low level features can be extracted easily. Then go for the little more detailed, then go for the more detailed one. So it is going by layer so that we can extract more and more features. Finally, all the features will be given to the fully connected layer. However, when we use the word convolution layer, in this case we are dividing convolution layer itself into 2-3 parts. We say convolution operation, then they are introducing the non-linearity. It can be ReLU function, also non-linearity. It can be sigmoid, it can be sigmax. There are many functions. However, I think in this case they are showing a ReLU function. That means anything which goes in negative side becomes a 0. You are able to see here the ReLU function has been utilized. Then they are also using the normalization of the parameter. Then comes a pooling. So they are using the word convolution, non-linearity, normalization, pooling, all together is a convolution. So this is, every author has a different way to represent. We say convolution layer is a one aspect, pooling is a next aspect. However, in this publication they are combined. Is convolution includes a convolution operation, nonlinearity operation, normalization and pooling also. So this is as I say, the author to author it varies. In my view, convolution layer is a separate operation, pooling is separate operation, fully connected layer is a separate operation, and then we need to learn all together. Now let's see from my point of view, this is input image. Again, input image I am showing only 0 and 1s. We already learned in a previous lecture that the RGB model, red color 0 to 255, then green 0 to 255, blue from 0 to 255. So those things a similar way we are using the word convolutional layer, we are saying pooling layer, and this is a dense layer which we call a fully connected layer. Now again we are saying in this case convolution layer is not only one layer, we are showing a sequence of number of layers. Similarly, pooling is also a number of layers, it's not one. And finally, after pooling, when we are converting we are giving this information to the fully connected layer, we are doing a flattening. What is a flattening? We'll also explain in this lecture. Now, that means we are going with input image, we are digitizing, we are converting to numbers, then convolution, then pooling, and then flattening, and finally go to the kind of model, a dense layer. So what we say, convolutional layer serves as the initial layer, and the fully connected layer is a final layer. Now possibly that we can have some sort of interplay between the convolution, pooling, then going back to convolution, then again pooling. There's a possibility. So these are the important, and as I mentioned very clearly, CNN layer complex, as the number of layers are increasing, complexity will increase. But initially we go ahead with a simple feature, then slightly more complex feature, then much more complex feature. So we go, as number of layer increases, the more and more complex feature can be explored. And then simple feature, we use a word also, as I say, that can be color, can be edges. So these are simple feature which can be easily recognized, and subsequent layer can be going ahead with the more complicated shapes of the feature. So this is a one, and as I mentioned also, the fully connected layer is a final or ultimate layer. Now here we are saying convolution layers can be many. Pooling layer can be many, but fully connected layer will be kind of, which is the interaction, will be one. Of course it can be then go for the many layers in that, it can be a number of hidden layers in that also. So this is what has been shown clearly here. As I say, fully connected, this is the connection only with a convolution and pooling layer. So this will be the only connection. After that everything is like a ANN. We do same model, similar kind of we have weighting factor, we have input factors, inputs coming from previous layers, pooling layers, and then we go with the weighting factor, we use the algorithm appropriately, we go ahead with the neuron, then neuron get activated using the activated function. It can be any function, it can be sigmoid function, it can be tan hyperbolic function, it can be ReLU function also. Now just to understand the weird debris, I'm just showing some sort of picture. This is a weird debris, computer will not be able to see it, and then when you show the computer will see in this form. As I say earlier, it is kind of a RGB model, and then finally conversion happens, right? So this is a very important, that what computer sees, we need to think from that point of view, how the grid data are getting generated. We need to think from that algorithm and implement. Are we able to do in one layer? It's very difficult. Reason being, many times it can be a different number. Here I'm showing this is a 1080 and 3 is a basically for RGB. Now any layer 1080 into 1080 will make a some sort of vector of something 1166400 long image vector. So this long image vector cannot be analyzed immediately. So that's why we need to go with the patches. We need to divide into patches and build on that, so that we are able to analyze appropriately. We can denoise it. We want to go ahead with the major information. That me, in this case, in this image, basically, if I want to reject this, I want to reject it, I want to reject it, so that more and more clarity comes into the picture. That's possible. That means we really require a good image analysis, so that we are able to classify a weird debris properly. Otherwise, with this weird debris, many other small weird debris will come. If we try to do that, there will be more problems. So classification will be difficult unless we do a pre-processing of the images. So for that purpose, we try to go ahead with the feature extraction, and that's why we say that we require a filter. Filter can be any size. It can be 2 by 2, 3 by 3, depends on what we want to achieve. And then we, after that, we try to shift by pixels. So this is the pixels, pixel 1 2 3 4 5 6 7, and then we need to shift the pixels, and whatever we do this kind of patchwork, that is called a convolution. Now we can think about the different weight factors. Different filters are there, and they are already inbuilt. We can design our own filter also, and then we try to extract more and more features. Now here the difficulty comes. We cannot do each and everything ourselves. That's why we need to go ahead the pre-trained ANN model, and then pre-trained ANN model which are available in the MATLAB. There are many. If we do not have, we can import also. We can install those model also. Reason being, we want to go ahead with some established tools so that we can extract the information which is more relevant to us. Now how this thing happen, I'm just trying to explain in one or two slide. I'm assuming this is a filter or kernel, more or less same synonymous they are using. So this is a filter, and then here is the image is a 5 by 5 image which has been shown here. Now first filter is trying to see only this portion, this patch. So what will happen, the filter will go with a dot multiplication, 1 into 1, that's why it has been shown 1 into 1, 1 into 0, then 1 into 1, then here 0 into 0, 1 into 1, 1 into 0, then here you can see here again 0 into 1, 0 into 0, 1 into 1. Now if you sum up, here the 1 into 1 is a 1, here 1 into 1 is a 1, all other are 0, 1 into 1 1, and 1 into 1 1. So this will be sum up, and that will give a 4. That means what we are doing here, convoluting the feature we are getting by multiplying filter with the first patch, and we get a result 4, and that's what we call as a convoluted feature. Now same thing, if I slide by 1, that means instead of this filter I move to this kind of thing, then I'll multiply, I'll get a second number here, then I get the next multiply one again, stride one more, I'll get a third feature. And similarly in this case, if I slide downward, I'll get this feature, another one, then I'll get this feature. So this is we will be getting from 5 by 5 is a kind of a 3 by 3 matrix that will be called the feature map or convoluted feature. So that is where same thing has been explained over here. We say convolution is a mathematical operation applied to input data using kernel or filter that has been shown here to generate a feature map, and everything is a computer work and they have memorized it, so they can go back also to get a results. So convolution operation basically is kind of moving a filter uh, across the input data, calculating that product which has been shown, and then getting some portion of input. It's not completely immediately applied. It is in this case particularly it was applied initially on this, next time it will be applied on this portion, next time it will be applied on this portion, then it will be applied by on this portion. This will be what we call a one stride one, but we are moving by 1 pixel. Now just to demonstrate that, now let's see stride I have taken 1, and this is the filter. So initially we are multiplying here, you can see here 1 into 1, it will be 1, minus 1 into 0 0, minus 1 into 0 0, minus 1 into 0 0, here 1 into 1, it will be 1, here minus 1 into 0 is 0, and here also 1 into 1, so it will be 1 1 1, it will be 3. So that's why we will get a dot product as a 3. Now we moved 1, as I say stride 1, the next time I will be multiplying 1 into 0, minus 1 into 0, minus 1 into 0, again minus 1 into 0. So first 3 it will be 0 overall. So overall summation here is turning out to be minus 1. So this is a kind of stride 1. Now coming to the stride 2, here we are moving this as a 1 block and this as a second block. Now when we multiply, initial block we are already getting 3, but here the second block we are getting 0, the 0 0 0 it will be 0. Next one we are getting here is a minus 1. Next one here again we are getting minus 1, here again we are getting minus 1. That's why we are getting results here as a minus 3. So here a stride was only 1, that means we were using only this block, and that's why here what was coming as a 0 in this situation. So the overall result was a minus 1, here is a minus 3. Now if we go with a similar kind of thing, we can develop a 6 by 6 matrix to the 4 by 4 matrix, and this is what result has been shown in this manner. Coming to the second filter, there was a filter 1, now the filter 2 will be getting slightly different feature map, and then you can simply multiply all those factors like a minus 1 into 1, 1 into 0, minus 1 into 0, minus 1 into 0, 1 into 1, minus 1 into 0. So in this situation we are getting minus 1 initially, then plus 1, then minus 1. So overall result will turn out to be minus 1. So in this manner we can get a complete feature map. Now we can go ahead with the RGB kind of a 3 channel. So we can say we can extract only the red image, we can get only the green image, we can get also on the blue image. And this is same thing which we had taught in a previous lecture. That's a lecture 26. We wanted to extract the green color, we wanted to extract the red color, we wanted to extract the blue color, and we showed in the lecture 26 how to extract the red color, how to extract the green color, and how to extract the blue color. Of course, in that time I mentioned very clearly, because of overlap we are getting some error in the blue color. So that was our shown in the earlier case. However, here manually we can operate and we can say, yeah, there is something wrong. We, if the here I have changed the line now. If I say now come up with a threshold, if the threshold is more than 230, then only you take an image, otherwise don't take an image. So this is the one modification I did for the blue color. Second thing is that we are removing here the 10 and then removing 9 also. Many times image when it is made what we call a zero padding, they add the zeros also, and then that's why the color get maybe we were getting a problem here, we were getting problem here, we were getting problem here. So the coordinate we change this algorithm by looking at the image where it is going wrong and then remove those features so we can correct the images. So wherever overlap comes we are able to do it manually. However, in CNN, because we have so many filter, and then if they have been pre-trained, because they have trained on a number of objects, maybe say thousands, naturally those algorithms are very important and we should utilize those algorithms. Here when we are doing modeling our own, then we are going feature by feature from understanding point of view. Otherwise, when we go for the something which is totally unknown, we need to go with a pre-trained algorithm and test those algorithm, and if it is not giving satisfied results, we should increase the number of samples. If it is again not giving good result, we further increase the number of samples of our training, because if even the 1,000 images are not giving satisfactory results, we need to go ahead with a more number of images. But we need to go ahead with some sort of fully trained algorithm. The way we are developing algorithm, it is good for the lower dimension, maybe say lesser number, and then because we can do a manual the intervention, we can really correct those images, but not the online kind of when we are going for online kind of monitoring. So what we have already learned now, here we say in case of the CNN, we have a 3 upper parameters. We say number of filter is a 1. We need to select the appropriate filter. Then we go for the stride. I have given example of stride 1 and stride 2, and we say very clearly the stride value of 2 or greater are generally not utilized. Stride 1 is only used. That means we need to move the filter by 1 pixel, and that gives a good results. Last one is a zero padding. This is a done zero padding. In the previous slide also I showed we removed the zero paddings also. Reason being the many times MATLAB introduce a padding to go for the image correction. So zero padding is also done many times to match input and output also. So that what is a zero padding? We say is useful for controlling size of output volume after convolution, especially when the convolution layers are deeper. This set all element fall outside of input matrix to 0. That is what we show there with the example. In this case you can see here input is a 4 by 4 and filter we are using 3 by 3. Even when output we get from this is will be 2 by 2. That means there is a mismatch between input and output. Now if I want to go I want input be 4 by 4 as well output be 4 by 4, and then we are also using filter. So what the MATLAB does, or maybe say even the CNN does, they add 0 or the outermost. That's what we say, outside of input matrix to 0. So you can see 0 here, 0 here, 0 here, 0 here, 0 here. So it's the whole circumference is surrounded by the 0, 0, 0. Now when we do the CNN operation, obviously convolution operation, using the filter 3 by 3, now this has a becomes 5 by 5. So now 5 by 5 can be converted to 4 by 4 using the this one, and this is a what we call a zero padding, often required to match input and output. It is being done automatically by MATLAB. Whenever there is a mismatch, we can do also intentionally, otherwise it will be done automatically by MATLAB. That's for the convolution, and we say three aspect of the convolution. Next one is a pooling layer. Why do we really require a pooling layer? We say the pooling layer is required to sampling, may reduce the size, something like where particle of this size need to be reduced to this size. So in that case we do a subsampling of that, and in the subsampling a pixel will not be lost, and major information will not be lost. That's what we are using the word here. So we say pooling layer, also known as a downsampling, conducts dimensional reduction, reduce a number of the parameters into input. Now why do we really require it? To reduce a time, and sometime we discard also the unnecessary informations. However, and we can go ahead with a number of thicknesses also. So that's why we are saying the pooling layers operate independently each depth dimension. Now the way initially I showed gear teeth, and we say many layers are, we are doing a slicing. If we do a slicing operation, that's similarly in this case every slice will have a separate pooling layer. Now just to demonstrate, I showed through the image, but I'm just trying to give some sort of a sketch here. Here you can see the size is 224 into 224. Third dimension I'm not changing. When we use a filter, and then we are reducing size to 112 and 112, that means it's reduced to 50%, and every layer by layer we can go ahead so that we preserve information and then continuously reduce it so that computational efficiency can be increased. So what we say here is subsample pixel to the make the image smaller, and then instead of going for many parameters, few parameters are selected for the further processing. So it's important for us to understand. Now in this situation, when we are going to the particularly pooling operation, we have a two type of the pooling operation. Here we are showing the max pool operation, where the filter size is 2 by 2, and then stride is also, in this case they have used a 2. The same procedure what we learn in a convolution layer. But what is this max pool? You can see this is the first one, where we are using the filter 2 by 2. In this situation we say that 1156. So we look at the what is the maximum value, which will be more important to us, that is stored over here. Then we have a 2478. What is the max value? Max value is 8, that is stored here. Then comes the 3212. What is the maximum value? 3, that is stored here. So 1034, here we are storing 4. So here the information uh, is reduced. So instead of 4 by 4 matrix, now we have a 2 by 2. It will be much more computational beneficial, or maybe the efficient. However, we also know we are going to lose some information in this situation. So we are ready. If we say the least significant information can be lost, we do not worry, then this kind of pooling will be fine. However, we mentioned that there are two types of the pooling, but what we have learned in earlier, the max pooling. There's another one called average pooling. In a max pooling, as I say, the filter moves across input. It selects a pixels with a maximum value to send to the output array. So here in this case, it has selected 20, and this is the output array. It has sent to the 20 over here. In this case, it has selected 30, and then send the output layer 30. Here in maximum value is a 1112, and then it has gone to the 11 over here, 112 over here. Here maximum value is a 37, it has gone to this. This is the max pooling. Now coming to the average pooling, it takes average of this. So the average of 12, 28 and 12. So this is what has been shown here. The average will turn out to be 13, that has been stored over here. Now here the in this case 3020, it will be 32 divided by 4, it is 8, it is has been stored here. Similarly in this case 34 plus 70 plus 112 plus 100, which is turning out to be average 79, that has been stored over here. And coming to last one, it is coming out to be average is 19.5, but it doesn't take a decimal, so that why it has moved to the 20. That means a rounding off 19.5 is a 20, and that has been stored over here. This is a what average pooling and max pooling. More people, most of the algorithm, they use a max pooling. As I say, that some information will be lost. You see, that's why while a lot of information is lost, a lot of information of some information now is a subjective, is a loss in the pooling layer, but it has a number of benefit to the CNN. So blindly believing the CNN will not be good option. We check for the few cases, and then if those are fine for us, then we go ahead with this kind of max pooling, reduce the complexity, improve the efficiency, and then often we say that it can avoid overfitting, which we have learned in earlier lecture. What is the meaning of overfitting? Finally, we say that fully connected layer, which we have already learned. In this case, you can see here whatever the matrix which comes out from pooling layer, it is need to be flattened. What is the meaning of flattened? Whatever this layer, it will be arranged first, then this layer has been arranged second, then this layer has been arranged here. So this 9, it has been 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has been arranged, and then those all elements have been connected with the neurals, or we say that in the fully connected layer. It's very important. Now, as I mentioned, in a fully connected layer, usually go has with the softmax activation function, which is kind of the sigmoid function with to some understanding. However, we have learned the sigmoid for the only two classes, 1 and 0, while this is a new one. The softmax is basically utilized for the multi-class classification. So that's why the different name is given softmax. It is basically for the multi-class classification. It's not only for the two classes, which was taught earlier in analysis, which we did in the lecture 23, that we will go with a sigmoid. And what we use, I learned that time, a logistic regression. Even though if it was not a regression, but we use our logistic regression, and we taught a sigmoid only as a 1 or 0 to go ahead and divide in two classes, something like a male female, while in this case it is a multi-class classification, and that's why we use a softmax. Now, what do we do? Which kind of methodology we adopt when we go for the this debris classification? We say that we capture all the images, and if possible try to denoise. It will be very important. As I mentioned here, that this is a noise, this is a noise, this is a noise, this is a noise. If you go ahead with all this noise, naturally it will be very difficult, and maybe like this is also noise. So whichever the particles, we try to go ahead with the better manner. Like in this case, there is a white background coming out, so it needs to be the denoise. And if actually we try to classify it in a general pattern. Now, what are the pattern and what kind of particles we really require? Now, you see, some author, they say only 4 particles, some authors say 3 particles, some authors say 5 particles, some authors say 7 particles. So however, we don't want to go in a detail of those. We are just trying to learn only. You say severe sliding, which is alarming. In the situation, classification may not be sufficient, so we can think about a sliding and severe sliding in one category. Fatigue may be in another category, cutting in another category. Once it has been done, it is kind of, we have divided into 3 categories, and based on the size we can say whether it's a severe sliding or mild sliding or ultra mild sliding. Similarly for cutting, similarly for fatigue. So we require both. It is not only the classification in the categories, but also what is the size, and the size also matters, and the shape also matters. Shape will give us a kind of wear mechanism, and size will give a kind of severity of the wear mechanism, and both informations are required when we go for this kind of algorithm. Now, and in this case, suppose we have a number of images. In this case, I am showing that in one of my laptop I have a 63 photograph of the wear debris. And then when I look at an initially, we say, oh, cutting, we have only 5 particles. Fatigue, I have only 25 particles. Sliding, I have a 15 particles. So in this case, cutting, I can use a 5 particles, and fatigue, we have something like a 25. Sliding, we have a 15. But when we go for the trained or already trained models, CNN models, in the situation, they go with equal number. That means whatever the cutting which is a minimum, I had to go also fatigue only with a 5, sliding also with a 5. Otherwise we need to go for the custom on the model which we need to generate. Now what are we showing in cutting? You can see here, this is a cutting particle, this is also cutting particle, this also, this is to some extent looks like a cutting. If I don't include it, can come as a sliding also. This is also aspect ratio is on higher side. So there is some sort of subjectivity from author to author. And another thing, it comes many times we generate as per the situation. We create a more abrasive particle. We generate a situation which causes a adhesive wear. We generate a situation which causes a fatigue wear. However, in the actual case, it can be mix of that. Adhesive wear may be leading to the abrasive particle. Abrasive particle may be going and getting embedded and maybe removing the surface coating and going for adhesive wear. Or adhesive wear is going for the fatigue, or fatigue is causing adhesive wear also. So there will be always a mix of this. However, once we train, we can get the, like this is a sliding particle, this sliding particle, and this is also sliding particle. It can be arranged. So this we need to go ahead with some sort of a methodology, some sort of arrangement, so the overall results are good. Now I'm just referring one of the article which has been published in Machinery Lubrication, where they analyze 800 images and then they made a 4 classes. They say cutting, mild sliding, severe sliding, and fatigue. As I showed earlier, when we going for the classification, mild sliding and severe sliding can be in a one category, and when we say severe or mild, it should come with a size. So again, can go with the main 3 category, and when we arrange from a particle sign point of view, then it can be mild, it can be severe. Also again, mild and severe can be subjective from one author to other author. So what they did, they tried to do classification. You can see here the cutting wear, and then they are saying this is a mild wear, this is a severe wear, and this is a fatigue wear. So they could divide into 2 categories. Number of particles coming into this is a kind of a cutting wear, and these particles are coming into this severe sliding, mild sliding, and fatigue wear. Then they further arrange from a size point of view, and then they are able to size, yeah, lesser than 100 micron is a mild wear. In my earlier slide I mentioned lesser than 25, it may be the mild wear, but more than 25 it can turn out to be severe wear. So author to author it can vary. That's why they are using the word here, threshold lesser than 100 microns. So this algorithms can be designed as per our convenience. Modeling can be done as per our convenience, or maybe the parts which we are using. If the gear itself is an size, naturally the threshold will be different. If it is in a centimeter size, if it is meter size, naturally the threshold will be different. So that's why we say that to distinguish fatigue and severe particles, the region the problem comes over here. You can see the fatigue where size and the severe sliding size is also almost the same. However, fatigue where you can see the different kind of cracks or maybe the fissures, while in this case these are elongated in one direction. So that's why we are using the word here, the sliding, severe sliding wear. And that's why he here says the 2 parameters related to surface characterization. One is what is granular surface composition of the fatigue wear will be different compared to the sliding wear. We are finding the straight line, but question comes, how the computer can find out those? Naturally we need to design parameters, we need to embed those parameters, then only the results will be favorable to us. That's why we say there is a considerable overlap between the fatigue and severe sliding particles. And then sometime we find also transition. Fatigue wear is leading to the sliding wear, sliding wear leading to the fatigue wear. So there is a some sort of transition, and then we need to really continuously watch, and then if we are able to take good pictures, and we are able to introduce a surface feature also, which will be covering in next lectures, particularly when we go for the surface design modeling. Those aspects will be very important. That will help us to go for the better wear production. We also published one paper in 2023, which was an online gear wear particle detection, and we going for basically categorization, not for size categorization. We use a CNN, and then we use a cascade classifier. In this case, we use a phi category. We say spherical particle. Mostly, it comes with shape and spherical particle, and which is much smaller in size. Also, cutting, fatigue, sliding, and rubbing. Rubbing is basically more on kind of friction side, and that the fracture will be slightly different. We use some sort of filters in that to then, find out the right image, and then we use also cascade classifier like the features to differentiate between the positive and negative image. So here this is also important. We go with the both positive, it looks like a fatigue wear, and we also go with the negative. No, it's not a fatigue wear at all. Is something like we are going with the complete thing. Yeah, it's a fatigue wear, it is not fatigue wear, it can be in between. So whenever there is a this kind of problem comes, there's some sort of transition, then we go with the probability. What is the probability? Is it a really sliding wear or is it a fatigue wear? So probability based also can be utilized so that the overall results are more favorable. We got something like accuracy of 97.4% after analyzing 506 particles. As we say that we divided in 5 year classes, and then we use in this case basically SEM images to, so it is again offline. An offline methodology is used to train our system so that future online monitoring can be done appropriately in real time. So what we did in this case, we use the activation function ReLU, and then max pooling also the filter is 2 by 2. Here convolution we use a filter 3 by 3. You can see the number of layers 200 that has been given here, the 200 filters. And then second convolution layer, which is next one, we use 100 layers. And then we also use a 50% dropout, the rejection rate of 50%. We use this back propagation so that to errors whatever we are getting can be rectified. After the max pooling we did a flattening, and so that we can develop a FC layer, particularly fully connected neuron layers, so that we can get a good results. This slide I'm picking up again from lecture 24, which already we have shown. Here we use a confusion matrix. You can see detecting or judging a spherical particle is not an issue. Then the judging cutting wear is also not a problem. The rubbing wear also is not a problem. The problem comes only in fatigue and sliding. The fatigue we get a one wrong, and then sliding we get a 3. So that's why with the this precision level decreases. This is a 94.75%, in this case 83.3%, and overall precision level is something like a 95.61%. And we also learn something recall in the lecture 24, and that is also more or less good, and that this is what was shown. We use a Neve classifier to do this kind of classification. Now last one, I'm just trying to give a this article which is published is particularly for wire based particles, and then they use DCNN, that's a deep convolution neural network. That's what has been shown, a DCNN. They use a 5 pre-trained models to classify in 7 categories. So some author they given 3 category, 4 category. We did a last time 5 category. Now this is 7 categories, and then they got accuracy of 88.39%, and they use a word something like a dense net 121. I checked in a MATLAB. Now they have a dense net 201, which has a convolution neural network of the 201 layer. There's another one, ResNet, which where I say the equal size is a must. They use a 50 layers for that. So these are already inbuilt MATLAB algorithms which can utilize to get a good results. So what is the future of this kind of VRW analysis or image processing? We say currently we have been utilizing 2D images to construct the VRW, but it has a limitation. We are not accounting the thickness. So that means we are not accounting going for the 3D approach, which can really give a very good results for this purpose, a particularly better model. And then we can extract the more information, which we can really go ahead with a better diagnosis of the machine conditions. This is very important. We go shift to the tool from 2D to 3D, but for time being we don't have that kind of features. And then we once we are able to do that, we can really extract the important features. We can develop better predictive models, and we can focus onset of the machine failures. This will help us to developing a better maintenance strategy, what we call as a proactive intervention of to mitigate any kind of failure. We say we want to just diagnose at the fault level itself. If there is a some misalignment, we are able to find immediately correct it. We did a analysis by misaligning the gear, and we found it the accelerated wear very high. That means even a slight misalignment can accelerate wear by 10 times or 100 times. If you are able to find out that initially in the beginning itself, we can correct it, and the life of component may be on a higher side. Actually, another one is that advanced image processing. We know we are trying to find out the particle which come maybe when the floating in the oil. Naturally, processing those particles also difficult. You first separate it and then process, and then again go ahead with the different angles, because for 3D imaging we require a different angles, so that finally it can be integrated, or we can go ahead with a better reproduction of the 3D model. 3D image doesn't come immediately, so we need to require a 2 views or 3 views to make a 3D image, which is important for us to. So that's why we see to go with the advanced image processing technique and automated methodology to enhance accuracy and reliability of the production model. Successful attainment of the data driven approach, particularly successful data driven models for the ware production, will help us better and better the proactive maintenance strategy, and we can optimize our machine performance. So we initially started ware modeling using only the few equations. Now we say that is it not sufficient, reason being those are the required for a failure analysis, or once we develop at the design stage they may help us, but in real situation things are much different. Even slight misalignment can change everything. So that's why we required a continuous monitoring, and then prediction also. Continuous monitoring alone will not help us, so we really require the predictive models. We required a 3D images of the particles which are coming out, which turn out to be very useful, because we can daily go ahead with the regeneration of the surfaces from where the particles have come out, and then we can estimate what will be the residual useful life with those kind of predictions. So I believe those are the futures, and then with the more advanced on the image processing that can be done, or at least I'm giving this knowledge so that the student can really explore when they are doing their projects, and then they can implement this kind of approaches. With this I say thank you.